Okay, so yeah, good afternoons. And last class of this module, are there questions about what was discussed earlier? Okay, so the landscape in this case, I mean, the Shrinkton-Kirkpatrick model is basically solutions of these equations. So basically, these are the self-consistency equation. That now we have this magnetization at site I. This is a variable, changes from one I to another. And this MI is determined in terms of the couplings, JIJs, and also the values of M at the other sites. This is sort of similar to finding a minimum of, well, it's exactly actually, in this case, it's exactly a minimum of this function, which is a function of all the M's. And this equation is just a stationary condition that you take a derivative of this with respect to M and you get this equation. So, I mean, you know, it's not no different from, let's say, if you have a system of particles where you have a potential energy, which is a function of all the particle positions. And you have to find a local minimum of the potential energy. You will get exactly this kind of an equation. And then the MIs will be replaced by the coordinates of the particle, X, Y, and Z, X, I, Y, and Z. If you're a three-dimensional system, then you have, for each particle, these three variables, X, Y, and Z. And your potential energy is written in terms of those variables. That's always the case. I mean, if there are many minima, then finding the global minimum is a difficult problem. In all of these cases. So here also numerically finding the global minimum is very difficult. The limit of temperature going to 0, all these M's become plus or minus 1. Temperature going to 0 basically means that you know, the hyperbolic tangent, there is a beta here, so that diverges. So depending on the what you have here, this M's could be plus 1 or minus 1. That is like finding the ground state of the system for a particular realization of these JIJs. So if you have a sample which has, let's say, 1 million spins, there are so many, I mean, n times n minus 1 divided by 2 couplings. They're taken from some distribution. And basically that defines your the energy, JIJ, sigma I, sigma J. And then you're supposed to find the values of the sigma i's or the sigma j's, which will minimize that energy. For finite temperatures, the sigmas are replaced by these continuous variables, which take values from plus 1 to minus 1. And you have a function which is a function of all these variables, all these continuous variables now in this case. And you are supposed to find the minimum of that function. So it's a generic problem that you have a function of many variables and your landscape is basically the local minima of that function. How many of these local minima are there? What are the depths of this minima? All those things are questions of interest in any landscape problem. And you also want to know eventually, if you want to do dynamics, then what kind of barriers one has to overcome in going from one minimum to another, all sorts of things like that. But I mean, the structure of the problem is exactly the same as you know, many other problems of this class. When this temperature is 0, then the degrees of freedom that you have is flipping a spin. Sigma I goes from plus 1 to minus 1. When you are have these continuous variables at a finite temperature, then the degrees of freedom are continuous changes in the values of these MIs. Are there? I mean, is that clear? I mean, you know, this is what is the landscape is all about. That you have a function of many variables, and to do low temperature thermodynamics, you want to find when this free energy is close to the minimum value. So then you have to find out the MIs, which will give you a minimum value, and how many such minima there are and how they are related to each other. All these things are properties of the landscape. So any other question? So this is the thing that, there are many solutions, etc., that gives you a free energy landscape. It is different from the landscape that typically one talks about in the context of particle systems, where one looks at the potential energy. It's not the free energy. The potential energy you want to minimize, and you want to find out what are the positions of the particles, which will give you that minimum or something which is near the minimum. Because the free energy for a particle system is, you cannot write down the free energy so easily. Here you can write down the free energy because you have infinite range model. So the kind of mean field treatment that I've been discussing, that leads to an exact expression for the free energy. For a particular GIJs, this expression is exact in terms of these MIs. Of course, this is just an expression, so the values of these MIs have to be determined from this minimum condition. This is just the first thing. Then you have to look at the second derivative and look at the eigenvalues of the Hessian matrix, and you have to look at whether all the eigenvalues are positive or not. That will give you a minimum. Particles also, but that will be approximate. I have done some work a long time ago using that framework, that there is this density functional theory that allows you to write the free energy as a functional of the local density. So one thing is that here you have a local, you have a lattice. So you have a discrete set of variables. But when you are doing a particle system, of course, there is no lattice to begin with. It's in continuum space. So, and the quantity that plays the role of this m's is the local density. So the free energy is a functional of the local density, and you have to do a functional minimization. And that can be done, but that treatment is not as good as this TAP, because the free energy that we are using is an approximation. It is not the exact free energy for a system of particles. Yeah, it's a mean field. No, mean field becomes exact for the infinite range models. That's the whole point. No? That's why one is looking at this infinite range model where mean field theory becomes exact. One could have written this down for a system where these JIJs are not infinite range. JIJs are nearest neighbor interactions or something like that. That also people have done. And then you get again a set of self-consistency equations. But that free energy is not exact for that problem. That free energy, when the JIJs are short range, the free energy that people would like down, the mean field free energy that one would write down, would not be an exact, exactly expression for the free energy of that system.
So, Chandan, so here also you can, from this, once you find the minima, I guess depending on initial condition, again, you can get
different
minima, and you can compute this P of Q, right?
Yes.
And that sort of...
that should be given by this Parisi solution.
Parisi solution. But that is different from the graph you showed, which is from direct modeling.
Yeah. So, so one thing that people have done, including I have done a long time ago, is to, you can calculate these MIs in a simulation, right? For some short time average. So you start with some initial value of the sigmas in your Monte Carlo simulation, go to some low temperature, and calculate the spin averages over a certain period of time, and then put that back in here to see whether these equations are satisfied or not. So that also, that also one can do. But then there's a little bit of ambiguity as to how do you calculate this MIs? You have to calculate the sigma i's over some period of time. If that period of time is large, then system may sample different values and so on and so forth. Then those MIs will not satisfy this equation. But
at low temperatures, it will be.
At temperatures low enough, then it will be stuck in a minimum, and then. So I mean, there is not much of a disagreement about these different ways of looking at this problem. One was the replica method that gives you this replica, this overlap between minima and things like that. And here one is directly looking at the minima of the free energy. So they give you basically a consistent picture of what is going on in this system. Okay, any other question?
The replica solution, is it specific to long range, or it's in general it can be for any?
The replica solution, I mean, you can write down you can proceed with the replica trick.
But it would have the same, that would be the structure one would.
Yeah, so it will be basically the thing that will not work there is that the saddle point will not be the right solution.
Oh, right, okay.
In the sense that if you have infinite range interaction,
right, okay. Yeah.
Then the saddle point gives you the exact solution. But here there will be fluctuations and one doesn't know how to take that into account. So, I mean, there are people have thought about that problem also. I mean, in the sense that in ordinary critical phenomena, what you do is you do mean field theory, and then you say that below a certain upper critical dimension, this mean field theory will not be exact. So then what can you do? You can do some RG and things like that, automative RG and stuff like that. That also people have tried for this spin glass problem. That short range models, then there will be some upper critical dimension, which is 8 in this case, as far as I remember. So, I mean, 3 dimensions, one doesn't get a lot of information from that kind of a calculation. So, all the methods that people do in ordinary critical phenomena have been tried in this context, because you have basically, after you replicate, then it's just like a standard spin problem. Don't have any disorder in the interactions anymore. You have some, but you have the sigma I, alpha, sigma j. Alpha is a new index that you have to take care of. But then one can do all the other methods. One can do high temperature expansion. One can do this RG calculation for the replicated Hamiltonian. All these things people have tried. Okay, so then we have done all of this. This is one thing that I just wanted to mention in passing. I mean, I will not give you a derivation of this or anything like that, but that is something that is very interesting in the sense that after one accepts this way of breaking replica symmetry and all that, then you see, whenever replica symmetry is broken, you have these values that pure states. For T bigger than TC, one has just this kind of a structure. T bigger than TC is basically where you have a paramagnet. There is only one minimum. But then, there is this, this breaks up into, as you go to lower temperatures, this breaks up into this non-trivial structure. As you go to still lower temperature, again, the structure becomes more and more complex. In the sense that the number of minima that you have, that increases as you go to lower and lower temperatures. At high temperatures, above the transition, there is only one minimum. And then as you go to T less than this critical temperature, you will have number of minima, which number diverges as n goes to infinity. But the way it diverges depends on n, will change. So there is this complex structure, this landscape structure, and then one can look at, for example, how the spin configuration or the M's, now this not the spin configurations because we are looking at finite temperature, how the M's at one of this minimum are related to, or how different they are from the M configurations that you have in another minimum. And that quantity you get from these overlaps. These overlaps I had defined earlier. These are the overlaps. When you have alpha and beta, so this notation should be changed because it's alpha and beta, they are also used for replicas. And that causes some confusion. So these are two different minima of the potential energy, and the overlap is just given by this. And it goes from +1 to -1, the way it is normalized. So the question is, if I now look at this picture and look at 3 minima, then you have this overlaps Q1, 2, Q2, 3, and Q3, 1. One is the overlap between 1 and 2, 2 and 3, and 3 and 1. The question is whether there is any relationship among these things. And what people have found is there is indeed a relationship, and there is this hierarchical structure, tree-like structure, which is called ultrametric structure. In the sense that these 3 numbers that you get, there are only 2 possibilities, where all these 3 numbers are the same, or you have this other possibility, that 2 of them are the same and the third one is larger. So this is something which is not expected from the beginning, but as one does the calculation, then this is something that comes out of the calculation. And this implies something like what is called ultrametric, which is something like a tree-like structure. Says that the overlap is determined by how far. So the overlaps, I mean, all this pure states or minima, etc., they form basically this kind of a tree-like structure, in the sense that one can draw this kind of a tree-like structure, which will say that this belongs to this branch of the tree, this belongs to that branch of the tree, etc., etc. And the overlap depends on how far up the tree one has to go to find a common ancestor. So if I look at, let's say, this minimum and that minimum, then if I want to go up the tree to find a common ancestor, then I have to go here and I have to go there. And for this, I have to go up here and then I have to go there, and then I find a common ancestor. So that requires 2 steps. If I want to look at only these 2 minima, then this I can go up here and I'll go up here. I'll find a common ancestor. That requires only 1 step. That tells you that the overlap between these 2 will be larger than the overlap between, let's say, these 2. Number of steps that I have to take to find a common ancestor, if that number increases, that basically means that the overlap decreases. So now, I mean, just leave it as an exercise to convince yourself that if you take any triplet, so if I take, let's say, this, and that, then for all pairs, 1, 2, 2, 3, 3, 1, you have to go up just 1 step. So then the overlaps will be the same. But then if I look at, let's say, 1, 2 here and a 3 there, then the overlap of this 3 with 1 and overlap with 3 with 2 will be smaller. Because if I take something from here and something from there, then again I have to go up 2 levels to reach a common ancestor. So the overlap between, if I take 1 and 2 and 3 there, then this overlap between 3 and 1 and 3 and 2 will be smaller, and the overlap of 1 and 2 will be larger. So then this will lead to this kind of a situation, that any 3 such states that you take, and if you say that the overlap depends on how far you have to go up the tree to find a common ancestor, then you can have only these 2 possibilities. And this is known as ultrametricity, and this is one of the sort of very interesting properties of this landscape that one gets for this spin model. We will have tried to verify this numerically, but it's difficult. I mean, there is no clear numerical evidence that this is satisfied, but there are other numerical evidences that says that this solution is actually a good solution. So this is just one of those evidences that I mentioned, that the distribution of the overlap here, one is not talking about 3 such states and 1, 2, 2, 3, and 3, 1, but just 1, 2, I mean, the binary thing. And there one finds something that looks like the Parisi solution. And this is something that says that in the thermodynamic limit, the Parisi solution is supposed to be exact. So that's all I'm going to say about this infinite range model. I spend a lot of time on this infinite range model because it does illustrate many of the interesting things about this kind of disordered systems, in particular the landscape that comes from the solutions of the TAP equations. And in this case, at least, one can say that the mean field theory that leads to this landscape that is exact, and one can calculate some things, but not always analytically, but numerically one can calculate some things. So the reminder of this, I mean, today is the last one, so I mean, I have 1 more hour or something like that. I will spend giving you some information about to what extent the behavior that I have just been describing, to what extent that is actually satisfied in real systems, real 3-dimensional systems. So this copper manganese or europium strontium sulfide, etc. So there are many such spin glasses that people study in experiments. So of course, it is important to understand to what extent the predictions that one gets for this infinite range model, to what extent they are satisfied in 3 dimensions. 3 dimensions, short range model. So if you have infinite range model, of course, it doesn't matter which dimension you are talking about. But as soon as you have short range interactions, then you have to specify the dimension, the spatial dimension in which these spins are sitting. So the first question that one would like to understand is that, I mean, this infinite range model, as you have seen, does exhibit a transition, does exhibit a thermodynamic phase transition, a continuous phase transition, which is somewhat peculiar in the sense that as soon as you go below this transition, replica symmetry is broken and all sorts of things like that. But there is a transition in the infinite range model, in mean field theory. But that doesn't necessarily mean that the model in 3 dimensions also will have a phase transition. So this is something that you are already familiar with, that there are some situations where mean field theory will say that there is a phase transition, like Ising model mean field theory will say there is a phase transition in all dimensions. But in 1 dimension Ising model, you don't have a phase transition. There is a lower critical dimension such that below that dimension, there is no thermodynamic phase transition. So the question is for the spin glass model, whether there is a similar lower critical dimension and whether it is above 3 or not. So, and that there is no sort of exact way of answering that in this problem. People have done a whole lot of numerical work, simulations, high temperature expansion, various kinds of real space RG and things like that to answer this question. And I think now people are reached a consensus that 3D spin glasses with short chain interactions do exhibit a thermodynamic phase transition. Since there is a transition that separates a high temperature paramagnetic phase from low temperature spin glass phase, and one can calculate what the temperature is where this phasing occurs depending on the kind of interactions that you have chosen for your short range spin glass models. 2 dimensions general belief is that there is no finite temperature phase transition. 2-dimensional spin glass models with short range interactions, they sort of similar to the 1D Ising model in the sense that there's a correlation length which diverges at 0 temperature. So it's sometimes called a 0 temperature transition, but you can of course go to the other side of the transition. But at low temperatures, then you see some signatures of this correlation length becoming large as one is approaching t equals 0. So that I think now there is some kind of a consensus on that 3D short range models will have a spin glass phase, whereas 2D short range models do not have a spin glass phase. They have some kind of an incipient transition at t equals 0. And so low temperatures, there are some interesting phenomena that one sees associated with that correlation length becoming large, but there is no spin glass phase as such. So then the question arises, let's say now we consider only the 3D spin glass short range interactions, where there is a spin glass phase. So the question is whether that spin glass phase has the properties that we have just discussed for the SK model, Shrunken Kirkpatrick model. In other words, the properties that are now, of course, quite non-trivial is this landscape. That there are a very huge number of local minima of the free energy. And as a result, you have to use this order parameter, which is a function of a variable, et cetera, to describe that phase and so on. To what extent that kind of a description is required for the 3D model with short-range interactions. And that is not settled yet. That question is not settled yet. That controversy has been going on for like 30 years or so. And there are many, well, these days the number of new investigations is small, but the main problem is that, again, this can be answered only numerically because there is no good theory for the 3D model. I mean, there are some theories which I'll tell you a little bit about. But for example, I mean, there is no theory which is sort of at the level of rigor as this theory for the infinite range model. For short range models, we don't have. I mean, we don't have a theory for the 3D Ising model to begin with. I mean, so in 3D, whether actually a phase transition occurs or not, things like that can be answered only numerically, or there are various other methods like high temperature expansion, low temperature expansion, and so on. So that controversy is still going on, and what is happening, I mean, these days is that if one wants to solve, so one has to basically answer this question from simulations. There, the main problem is the usual problem that you have in studies of glassy systems. That here we are talking about the spin glass phase. So one is talking about relatively low temperatures, and there it's very hard to reach equilibrium, in the sense that that's one of the properties of glassy systems, that relaxation occurs very, very slowly. So one requires very large simulations, large system size as well as long times. And in Italy, there is a special purpose machine that people have developed, and Parisi has been involved in that, Parisi and some of his colleagues. And they are doing these huge simulations, large systems and very long times. And then from that, they try to basically resolve this question, that whether the results that they are getting are sort of consistent with either this the picture that one gets for the infinite range model, or some other model, some other theory, which is here. I'll come to that in a minute. But unfortunately, again, I don't think there is a consensus. The numerical results that have come out from that project can be interpreted in different ways. And there is no sort of unequivocal evidence for this kind of picture, replica symmetry breaking, that one finds for the infinite range model. So what are the alternatives? So again, since time is limited, I will not go into the details, too many details of this alternative theories. And these alternative theories are also somewhat phenomenological. It's not that they're starting from the microscopic Hamiltonian and then trying to calculate free energies from that, calculated thermodynamic quantities or dynamics and things like that. They have in mind some kind of a picture, and the picture that is sort of painted by the Parisi solution is this complex landscape, that there are a huge number of pure states, and the behavior in low temperatures, at low temperatures, is governed by the property of this landscape. Alternative that is present in most other phase transitions that people have looked at is that the landscape is not that complex. And if the landscape is not complex, then the behavior that one expects is quite different from what one gets from the infinite range model. And in particular, this Daniel Fisher and David Hughes, they have been they have put forward a picture which is an alternative to this landscape paradigm, which goes under the name of droplet picture. So I'll just tell you in words some of the basic ingredients of this droplet picture. So they are saying that this business of having an not exponential, but a very large number of nearly equivalent solutions of the TAP equations, etc., doesn't apply to short-range models. And short-range models, the phase space is actually quite simple. Well, not quite simple, but simpler than what is predicted by this infinite range model, that there are only two pure states. Just like, in a Ising model, in a non-disordered Ising model, below the transition, there are only two pure states. One corresponds to all positive magnetization and one corresponds to negative magnetization. And Y2, and this 2 is related to the symmetry of the problem. The symmetry of the problem is that if I change the signs of all the sigmas, then the energy doesn't change. So this up-down symmetry that you have in the Ising Hamiltonian. And that says that if you have a phase where you have positive magnetization, then you must have another one with negative magnetization, which you get by reversing all the spins. So there are only these two pure states. That is the assumption in the picture that is developed by Fisher and Hughes. And then you have to look at excitations. This is another thing that in many-body physics, in all such many-body, all such problems where you have dealing with a large number of particles which are interacting and so on, often it is very difficult to do exact calculations, as we have seen. But you can say something about the low temperature behavior if you know what kind of phase you're talking about and what kind of excitations are there. Just like, when you talk about magnetic systems, there the low temperature phase is an ordered phase. Ferromagnet, it is where all the spins are fairly aligned with each other. And then if you want to look at the low temperature properties, then one way of doing that is to do spin waves. The spin waves are low-lying excitations of that system. And so if you know something about the properties of the spin waves, then from that you can get some picture or some results for the low temperature properties. So here again, the same sort of thing is being done. Of course, here we are talking about a discrete system, so there are no spin waves, but there are excitations. Just like, you can think about again the Ising model, a ferromagnetic Ising model, where let's say you are in the phase where majority of the spins are up, positive magnetization. So that is the ordered state. And then if you want to study the properties of the ordered state at low temperatures, you can do something like a low temperature expansion, where you look at excitations. So basically then the excitations are clusters of spins which are reversed relative to the other spins that you have in the background. So here also one can try to develop such a description. So that is what this Fisher and Hughes tried to do. That again, they're saying that there are these two pure states related to each other by global spin inversion. But then at low temperature, system will be near one of these states. And then if I want to understand the low temperature properties, then I have to look at what kind of excitations are present at a finite temperature. And they then made some scaling assumptions about this nature of these excitations. And for discrete spins, the excitations are basically where you have flipped a certain number of spins. Or if you want to talk in terms of m's, you reverse the sign of m for a particular subset of the spins. In the Ising model, if I want to again look at excitations, then I'd look at, let's say, at very low temperatures, you have a situation where all the spins are lined up. And then from that, if I want to look at an excitations, I will take some of the spins and then flip them in the other direction. That will give you an excited state. So the same sort of thing one can think in terms of this problem. let's say, I mean, if you really want to talk in terms of very low temperatures, you have found the ground state of the system. And there will be two such ground states which are related to each other by global spin flip. And at low temperature, system will be near one of these ground states or the corresponding free energy minimum. And the excitations will be then clusters of spins, which you flip relative to this, whatever you had in the ground state. So is that concept clear? I mean, this is what?
So this only two states, because instead of large number of minima, it's like only one minima is kind of playing a role. Is that?
That is the claim. I mean, again, one has not seen it in this way or that way, in the sense that one cannot calculate in some sense how many minima there are, how they are distributed in energy and so on.
But finally, they are saying that, I mean, if I take a short range model with what JIJs, if I minimize the energy, I mean, like if I find at low temperatures only sort of it's in kind of one.
Yeah, so there will be excitations from that. I mean,
right.
And this excitation spectrum extends all the way to zero. Just like, again, if you have spin waves in Heisenberg ferromagnet, for example, again, spin wave energy can be arbitrarily small. So there are excitations, but those excitations are rare. Are rare. Okay. So they say that the excitations will be clusters, and these clusters excitation energy will depend on the size of the cluster, and they assume some kind of a scaling form for the distribution of these excitation energies, which extends all the way to zero.
So on ferromagnets, it will be again like it will depend on the domain wall perimeter or whatever, but here it will be some more
complicated function. Yeah. So this is the so I mean the picture is similar to what you have for a ferromagnet, except that since the states from which you are looking at the excitations, these are very complicated states. So if I want to look at low energy excitations, so the excitations will be also somewhat complicated. Ferromagnet, for example, if you want to have a region where the spins are reversed, to minimize surface tension, it will be sort of like a compact region. But here, that may not be so. The boundary of this cluster may be fractal and things like that. So these are all these things that are said, but the issue is whether that actually happens in this system or not, that has not been verified. But I mean, I'll just tell you about the basic assumptions. The basic assumptions are this reversal of clusters of spins, and the clusters will have a particular size. So if you have a cluster size L, then there is a characteristic excitation energy that if you reverse such a cluster, and this, I'm just saying that the cluster size is L in the sense that the number of spins in that cluster is L to the D. I'm not saying that these are very compact clusters and things like that. Not saying anything about the boundaries and fractal dimension of the boundaries and so on. So these are all sort of simplified picture. Then you have a typical So, I mean, all of these things have analogs in simple ferromagnet. If I reverse a cluster of size L, then I have to create a domain wall that separates this cluster from the rest of the system, and then this theta will be basically d-1. But here, these clusters are going to be very complicated, and if I look at the boundary, then in all cases, some cases you are breaking bonds, and in some cases you are actually there was frustration to begin with, so the energy actually goes up or down and things like that. So this exponent theta is going to be much smaller than d-1. That is the claim. But they don't say that what this value should be. There are some bounds on this theta. d-1 is the upper bound, and they say that d-1 by 2 actually the upper bound is d-1/2. There is some argument which I don't want to get into. It's a fairly complex argument, but they don't know the ideal. The point is that at this point, this theta exponent is not known. Only there are some bounds, and theta exponent can be quite small, which basically means that the excitation energy can be small, in the sense that even if you create a cluster excitation fairly large, then the energy associated that we'll need to create this excitation can be much smaller than what you need to do for usual ferromagnet or antiferromagnet. So there is this one thing, and then there is a distribution of excitation. This is the typical excitation energy. There is a distribution. And this distribution has non-zero weight. At 0. So although the typical value will require a certain amount of energy there for a given system, because of this strong disorder and so on and so forth, this will not be always a number, but there will be a distribution. And this distribution goes all the way down to 0, which basically implies that there will be some clusters that one can excite with very little energy. So at low temperature, the properties will be, in some sense, complicated because of these excitations are present. So this is one thing. The other thing is that barrier height. So to flip such a cluster, of course, one has to go through intermediate states, which will have higher energy. So there will be a barrier associated with the flipping of a cluster, and this barrier height goes as some L to the power psi. So these are the two main assumptions, that there is a
between the two symmetry related.
So I mean, the picture is that you have this is your whole system. And let's say here you have this one of these clusters that one is talking about with some size, and that basically means that in the ground state, let's say this had a picture in this region. There was a picture of the spins which are like this, and then this cluster basically means that what you have done is you have reversed all these spins, and that gives you an excited state. In the process of reversal, in the sense that going from this state to the state where all of these things have been reversed, energy in between will be higher. So going from the original, let's say, ground state, where this was the orientations of the spins in this region that will eventually become a cluster, there is some energy, and then you reverse all of these, and you get another energy. The difference is basically this excitation energy.
Right. So that is L to the power theta.
Yeah.
And
in going from the original state to a state in which you have this reversal, indeed, the system has to go over a barrier which is bigger than. I mean, the intermediate states will have energy which is bigger than this, the energy that you have here. That you can see. I mean, there are small clusters that you can construct such that if you reverse all of them, then you get energy which is sort of similar to what you had originally. But if you want to reverse this by single spin flips, then you have to go over intermediate states which will have higher energy.
So for ferromagnets, this should be exponential L, right? This is barrier height.
Ferromagnet, let's see. So ferromagnet, what you want to do is basically.
Oh no, this is not the excitations you are saying.
So this is the
for the excitation, the barrier for the excitation.
Excitation, yeah.
So that's different.
So there, let's say everything was up. this is the state that you are looking at. And you are looking at this region where you want to make this. So the energy difference will be basically the perimeter. But going from, I mean, if I want to start from here where everything was up and then end up with a state where everything is down, I have to go over, I mean, the energies of the intermediate states will be higher than the energy of the final state. So these are the two things. This comes in, I mean, because eventually you want to do dynamics. So these are the two ingredients of the theory, that there is a scaling behavior of the energy with respect to the size of the cluster, and there is also some sort of a scaling behavior of the barrier in terms of the size of the cluster. And this size and thetas are not known, not given to you, but there are some bounds on this size and thetas. And what they have done is then they have worked out the equilibrium picture as well as some things about the dynamics on the basis of this picture. No, there are all possible values of L. You see, just, I mean, if you want to think in terms of the original Ising model, ferromagnetic Ising model, I can have excitations of all sizes. The standard thing that you learn in class is that this is the ground state. And if you want an excited state, the first excited state is like this. This is what you learn when you do the low temperature expansion. So this is the cluster of size 1. But I mean, there are all sorts of other states where instead of just flipping one spin, you have flipped some L to the D spins. And in the Ising model, it's simple because you can calculate things exactly in the sense that, you know, if you have flip L to the D spins, then what is the lowest energy state that you have where L to the D spins have been flipped. This is something that we just drawn here, where you have a compact cluster. Inside this compact cluster, you have the spins flipped. And then you can calculate what the energy is and what is the path that one has to take to go from the original state to that state, and what are the states that one encounters in that path, etc., etc. But here the problem is complex because, first of all, the background is not like that. The background is where the spins are oriented randomly because you have this positive and negative interactions. And as a result, you know, even if I look at a ground state, in the ground state itself, there will be bonds which are frustrated. And so, I mean, you know, if your cluster boundary goes through those bonds, then you're actually reducing the energy by flipping those spins. So in some cases, when you flip the whole cluster, some cases you are even along the boundary, some cases you are actually breaking bonds, in some cases you're creating bonds. So that makes the whole thing much more complex, and one cannot get exact results for these exponents, theta, and things like that.
So you said that there are excitations which cost very less energy, and there's a finite density of those kind of excitations. So which means, in some sense, is it that it's not so frozen?
It's not so frozen, yes.
Okay.
So there will be non-trivial dynamics even at very low temperatures. And there will be dynamics associated, slow dynamics, because this barrier heights in flipping one of these clusters that itself assumed to scale with the size of the cluster. So, and just from this sort of fairly small number of assumptions, one can get some scaling picture for the statics and the dynamics at low temperatures. This doesn't allow you to calculate, for example, what the transition temperature is going to be, doesn't tell you much about the critical behavior, all those things. It's just a description of the ordered state, where you are assuming that the structure of the minima, basically, where you are assuming that there are only two pure states, only two minima of the free energy, and then making some assumptions about the excitations from those minima. So there is this issue of this free energy minima. I mean, the energy minima are something that are very well defined. And you have a function of some quantities like the spin orientations, and you can always look for minima of that. And one can find a large number of local minima and stuff like that. But for free energy, this issue of multiple minima is actually problematic, in the sense that in mean field theory that happens all the time, but then you do something like Maxwell construction to get rid of multiple minima. Like if you do the Van der Waals theory and things like that, there you find that there are multiple minima. It's a mean field theory. But then you say that short range system, this multiple minima business is not right description for long enough times. Short times you can still think of it like that, because I mean, even in first order phase transitions, when you have this hysteresis and things like that, but those are short time phenomena. That at short times you can still sort of think in terms of different local minima of the free energy, but at long enough times where you expect to have equilibration, then this is a little somewhat problematic to think of very many minima. These two minima, of course, that happens. I mean, symmetry-related minima that is allowed. That has to be there in the theory. So the fact that you have these two pure states in an Ising-like system, that comes from just the symmetry of the problem. But other cases, I think when you are doing averages over relatively short times, then one can think in terms of multiple minima of the free energy. But at the level of equilibrium, that causes problems. That is problematic. No, there are all these issues of convexity and so on. No, equilibrium state is supposed to be convex, but if you have multiple minima, then there are states in between which are not convex. For a sort of ferromagnetic model, pure systems, non-disordered systems, one gets around this by saying that these two minima are separated by infinite barrier, etc., etc. So then if you start near one of the minima, then there is no way that one can actually sample the states that are near the other minima. But here, for the mean field models, these barriers can diverge in the sense that that's one thing that I have told you about. That's the TAP equations. If you look at minima and different minima, some of them will have divergent barriers. So there again, it makes sense to talk in terms of multiple minima. But for short range models, that's problematic because, as I just told you, that just like when you have first order phase transition, then people talk about this metastability, but this metastability is only a finite time phenomenon. You can always have nucleation events, which will take you from one phase to the other. And there is no infinite barrier. The barrier can be large, but there is no infinite barrier. So the question is here whether this picture that is coming out of the mean field theory for the SK model, which has this multiple minima separated by infinite barriers, whether that can be substantiated for this short range model. That is what these people are questioning. So this is one description. As I said, it is a phenomenological description where one is making certain assumptions about the nature of this low temperature phase. this low temperature phase exists in 3 dimensions that people have found numerically, etc., etc. But what are the properties of this low temperature phase? That is still controversial. This is one set of predictions. Other is sort of similar to this replica symmetry breaking. This hierarchical organization of pure states, etc., etc. And which one is correct is something that is still under discussion. So these are the 2 main contenders, actually. This replica symmetry breaking, as worked out by Parisi, and this other kind of a phenomenological scaling picture, which is worked out by these people, and also a few others, Macmillan and Peter Young. All these, several people were involved in this. And which one is the one that gives you the right behavior is not clear. There are some people who, now the second one, I mean, this Newman and Stein, they have also written a large number of papers on this, but not recently. They are in the 90s, and some of them are also beyond 2000, but around that time, that there may be some mathematical objections. I mean, this is just what I was referring to. I don't understand those things very well, but there are some mathematical issues with saying that even in a short-range model, you can have that kind of structure that is predicted by the replica symmetry breaking theory. And then they have come up with some proposal, which again, as I've just written down here, we have many pure states, but the overlap is 0. Whereas in the Parisi picture, you have this distribution of overlaps that I told you about. And apparently, this way one can avoid some of the mathematical issues related to having infinitely many pure states.
But I mean, just from Monte Carlo simulation, if you compute this overlap distribution, what do you get? I mean,
Monte Carlo.
distribution.
You do get a broad distribution. It is not, like what you have in the pure Ising model. By pure Ising model, you will have this 2 kind of delta functions, which are plus m and minus m. But you see, I mean, that can arise from a distribution of overlaps a la Parisi, or you can also have this. I mean, since there are cluster excitations, which have energy close to 0. So in one of the, I mean, what you do is basically in that simulation, you run two simulations in parallel with 2 different initial conditions, right? So it's possible that one of them goes to a state where one such cluster has drift, and the other one goes to a state where this to the actual pure state. So then the overlaps will will not be large, because it depends on how big a cluster has drift. So one has to do very detailed analysis of this simulation data, which people try to do, but the funny thing is that then maybe depends on which group published the paper first. Somebody writes a later paper based on numerical simulations saying that these simulations provide evidence for this picture. Then the other camp will write the same data. They will write another paper which says that they can make these observations consistent with their picture also. So that is what has been going on. I mean, you probably remember this. We had this Parisi meeting where Parisi was asked, I mean, is there any sort of clinching numerical evidence that says that this kind of RSB picture is valid in short-range models or not? And he didn't give a clear answer. He said that people are trying to do this numerically, but there are problems with very, very long time scales and equilibration and this and that. So I think it is fair to say that now, till now, there is no very clear evidence that says that either this picture is right or the other picture is right. And one more thing that people have tried to do, and this is something that people have tried to do experimentally also. So in this picture, since there are only two pure states, sort of like the ferromagnetic Ising model, you know that the ferromagnetic Ising model does not have any phase transition when you apply a magnetic field. The magnetic field basically kills the phase transition in the ferromagnetic Ising model. The same thing would happen here, because here the two pure states are related to each other by spin flip symmetry. And as soon as you put in a magnetic field, that symmetry is lost. So there is no sort of bifurcation of phase space and things like that that you would have in a phase transition. So this theory would predict that no Almeida-Thouless line. If we remember, I had given a phase diagram where in the phase of temperature and magnetic field, there was a line saying that as you cross that line, replica symmetry is broken. There is a phase transition. But according to in this picture, as soon as you apply a magnetic field, the phase transition that you had in the short range model, that disappears. That so I mean, this is something that people have tried to do from experiments. That you can always do an experiment in a magnetic field, and then the data that you have to analyze in such a way to figure out whether there is a phase transition or not. And still, as far as I know, the evidence is not changing. Okay, so this is basically a summary of what happens in short range models. Still a problem of interest to many people, but it's a very difficult problem. So people basically get tired of working on it for a while, and then at this point, not many people are actually working on it. Then there are a whole set of problems associated with dynamics. I didn't talk about dynamics at all. I was just talking about equilibrium behavior because, again, you know, there are a huge number of things that one needs to work out to try to understand the slow dynamics of these systems. I've just mentioned a couple of papers which are very important. One is Tompolinski and Zepelius, where they worked out the dynamics of this SK model, at least, you know, dynamics within one of these minima, one of these pure states, near one of these pure states. And then there was a very influential paper by Kuliandolo and Kurchan, where they were looking at the aging behavior. This is something that I told you about. This is the non-equilibrium dynamics, where you quench a system from high temperatures to low temperatures and then see how it evolves towards equilibrium. This they did for the spin models, not for the Chandan-Kirkpatrick model. And then there are many other things, and you know, if you want to really go into it, there is a collection of articles. This is actually one of the Lejeune schools, and there was a lecture given by Laetitia in one of the schools, and her article actually is a very comprehensive article about what is known about this up to that point. I mean, still it's not very recent, but at least to begin with, one can look into that. And I told you that one of the sort of, in some sense, the main features of one of the most important features of this spin glass is this slow dynamics. I told you about this difference between different way of preparing the system and so on and so forth. So if one wants to understand that, then one has to sort of follow the developments that are discussed here. So this is all, as far as spin glasses are concerned, I think this is all I wanted to discuss. Maybe, you know, Abhishek can get Laetitia to come and talk about the dynamics of this disordered systems one of these days, because that's a whole different field altogether. Oh, right, she was. Mhm.
Sir,
So, yeah.
sir, I have like hysteresis in spin glass phase. How is it possible, sir? Because like magnetization is always zero, right? So are we talking about the local, like we take a particular spin state and then we look at the average magnetization at that particular site?
No, I didn't quite understand what you're saying. So, which quantity are you referring to here?
Magnetization, sir.
Yeah, the global, yes, the
Yes.
magnetization of the whole system is zero, yes.
Yes. So in hysteresis, we talk about how magnetization changes with the applied magnetic field. So in that sense, we won't be able to see hysteresis in spin glass
No, no,
phase.
no. But as soon as you apply a magnetic field, there will be a magnetization. As soon as you apply, so the magnetization is zero because again, you have both plus and minus interactions, and the spins can have positive and negative values, etc., etc. There's a whole symmetry. Symmetry is this plus minus symmetry, but that symmetry is there only when the magnetic field is equal to zero.
Oh, okay.
As soon as you put in a magnetic field, you break that up-down symmetry, and any system will have a non-zero magnetization as soon as you have a magnetic field.
Right. Yes, sir.
So then you can think of doing an experiment where you start with zero magnetic field, you ramp up the magnetic field up to a certain value, and then come down. This is what one does in hysteresis, no?
Yes, sir.
Cycle a magnetic field. So that same thing can be done here, and one can follow how the magnetization is behaving as you are cycling the magnetic field.
Yes, sir. Thank you. Yes.
Any other question? Okay, so there are some things other than this that I thought if I'll discuss if I have some time. So so now and also maybe in the if I have some time in the tutorial later on, I'll talk about some other systems which have similar behavior. So just to conclude, I mean, we have been spending a lot of time on this Parisi solution and its characteristics and so on and so forth. So the question that one may ask is that why are we paying so much attention to this? Because it is not clear whether that behavior actually is realized in three-dimensional spin glasses. The actual experimental system may not actually behave the way that this Parisi solution tells us about. But I think that still it makes sense to discuss this because it brings into focus many different ideas, many new ideas, and this is one case where one does have an exact solution, and all these things are very new. Order parameter function, symmetry breaking, replica symmetry breaking at the transition. Then, as I just told you, this ultrametric organization of these pure states, which is coming from this tree-like structure of the organization of the pure states. All these things are new. They may or may not be realized in short-range spin glasses. But if they are, then of course it's more interesting. If they are not, still I think it is quite interesting to look at these things. And what is even more, why people are now still paying a lot of attention to this is that this is a new paradigm for treatment of systems with this landscape business. There is one case where one can show that there is a non-trivial landscape, and one can also basically develop an analytic method for taking into account this non-trivial free energy landscape to get some answers for the behavior of thermodynamics, dynamics, etc. So what I'm going to do in the next 10-15 minutes is to give you some examples of other problems which are of current interest, where similar landscape picture has played an important role, where this landscape picture has led to some understanding, some developments, etc., etc. Again, this there are many such examples, and I will just talk about maybe one or two such examples. The most common example is glass. I mean, I've been referring to this in the lectures, in the sense that this is the original glass in some sense. I mean, the word glass came from the behavior of these materials, where, I mean, this is something that everybody knows, so I will not going to spend a lot of time on this. So glass is basically, you get a structure which is disordered, doesn't have the nice crystalline order that you have in a crystal, but it still behaves like a solid at low temperatures. And as the system goes from the liquid to this glassy state, in that supercooled liquid regime, one finds very slow dynamics. And so these are the two sort of characteristics of glasses that I mentioned, that the structure is disordered, doesn't have the conventional kind of long-range order that one has in a crystal, or in the case of a spin system, in a ferromagnet or antiferromagnet. So that's one thing. The other thing is that this slow relaxation. So in the glasses, structural glasses, viscosity, I mean, if you're, as you're approaching the structural glass transition, then the viscosity increases by a huge amount. And at least, you know, the measured values of this viscosity as a function of temperature can be fitted to a particular form, which is called a VFT form, which predicts a divergence at some temperature T0. So this suggests that there might be some, you know, real transition taking place at this temperature T0. But of course, I mean, experimentally, one cannot go all the way down to this T0, because the viscosity will be so huge that will not be able to measure it. And the other thing that is important, again, is that there is some excess entropy in the supercooled liquid state, and this relaxation, or the characteristic time scale, can be related to that excess entropy. So these are experimental facts, and which make the systems important. That the time scale or the viscosity, they grow rapidly. And it's not just simple Arrhenius behavior. This growth seems to predict some kind of a temperature where this would actually go to infinity. Not Arrhenius would be this T0 equal to 0. Then the only way you can get infinite viscosity is at 0 temperature. But here, experiments suggest that for a certain class of liquids, which are called fragile liquids, one has this behavior. And this divergence, apparent divergence, can be related to the vanishing of this excess entropy. The excess entropy, you see that this tau would go to infinity when this excess entropy goes to 0. So there is some connection between the dynamics and the equilibrium behavior that one found. I mean, there is, again, controversy about whether Adam-Gibbs is always satisfied or not, whether VFT actually works or not. So, you know, these are issues that are still there. But large class of systems, one has this behavior. This is the behavior that I'm talking about. The log viscosity as a function of inverse temperature. Arrhenius would be a straight line in this plot. Now you see a substantial curvature, and those are the fragile liquids, and there this VFT form is supposed to work. And here is a picture of this Adam-Gibbs relationship. As you can see, some liquids here that the excess entropy one can measure, and the time also one can measure. And this relationship that one has here is satisfied in some of these liquids. So then, you know, the question is whether the spin glass kind of developments that I have been telling you about, whether that gives us some understanding of what is happening in these glasses. And there, in the spin glass, we are talking about the free energy landscape, but here, as I said, you know, the free energy is not such a well-defined quantity, in the sense that one can write down approximate forms of the free energy, but those forms are not exact. Whereas for every model that you look at, the potential energy is, there is no controversy about that. If you know the positions of the particles, then you know what the potential energy is. So then one can look for minima of the potential energy. And you have this complex structure, landscape picture, and this landscape picture has been quite influential, and it has helped in understanding what happens in this structural classes. So this is one class of problems which are still quite relevant in the sense that nowadays, even now, a large number of papers are coming out on the behavior of the supercooled liquids near the structural class transition. People are working on improving computer algorithms. People are working on the development of some theoretical ideas and things like that. So this is one class of problems where the spin glass way of looking at things is important. Let me not go into this in detail. So I mean, people, this is just to show that we also did some work again some time ago on this, where we are trying to test this Adam-Gibbs relationship, where numerically one can calculate this relaxation time and the configurational entropy. And again, one finds something that works reasonably well. But of course, in real experiments here, we have maybe 3 orders of magnitude. In real experiments, we have 10 orders of magnitude. So the evidence is much more, in some sense, believable. But now, just to make a connection between this and specifically what I have been telling you about spin glass models, the connection is something that I had told you about a little bit in the tutorial yesterday, that here we are talking about Ising spin glasses with interactions between 2 spins. But people have looked at more, in some sense, different kinds of spin glasses. The first papers were done by Kirkpatrick, Tirumalai, and Wallines, and then Padisi, Mezar. Many other people also have looked at this, where one is looking at spin glass models, but they are different from the SK model. These are still mean field models in the sense that still they have infinite range interactions, only that in that limit, it is possible to actually work out the behavior explicitly. So infinite range models, but instead of Ising spins, you can have Potts spins, where at each site, the variable that you have, instead of having just 2 values, +1 or -1, can have 3 values or 4 values or whatever. So they're called 3-state or 4-state Potts models. Or you have Ising spin glasses with multi-spin interactions. One example I showed you, where you have sigma I, sigma j, sigma k kind of interaction. And people have worked out then the behavior of these things. And there, as I said, the phenomenology is a little different from what you have in the Ising spin glass in the Shelton-Kirkpatrick model. There, one finds basically a characteristic temperature, which is called the dynamical transition temperature. And thermodynamics at T less than dynamical transition temperature is governed by an exponentially large number of local minima. So this kind of a non-trivial landscape that we got from the TAP equations, these models also show a similar landscape. One difference is that you have an exponentially large number of local minima. In the sense that in the TAP case, the number of local minima would still diverge in the large n limit, but it will not diverge exponentially. So if you take the log of the number and then divide it by the number of spins, then when the number of spins goes to infinity, that would go to 0. There is no extensive configurational entropy there, but these models exhibit exponentially large number of local minima. But these minima are not so important in some sense thermodynamically. So, but for this temperature less than this dynamical transition temperature, there is a configurational entropy. That is basically what this tells us, that exponentially large number of minima. So that gives you configurational entropy per spin, which is non-zero. But this configurational entropy per spin goes to 0 at a lower temperature. And then there is a thermodynamic transition. And this is the transition that is described by one-step replica symmetry breaking. So this is a phenomenology that has been established by many people who are studying these models, that this is random first-order transition theory, where one is again looking at a spin glass, but of a different kind, where one has in temperature range, in temperature between this dynamical transition temperature and this static TS. In between, you have extensive configurational entropy, and that configurational entropy per spin vanishes at the lower temperature. And there you have a thermodynamic transition, and that is this random first-order transition theory that we just discussed. And this vanishing of the configurational entropy is similar to what I was telling you here. In structural glasses, this excess entropy goes to 0 at a temperature, which turns out to be close to this temperature where the dynamics diverges, are supposed to diverge. So this transition often is called, if one believes this Adam-Gibbs relation and so on, this is called an entropy vanishing transition. And a similar transition is seen in these models. In these models, also Minfield model, but they show a finite configurational entropy as long as your temperature is less than this dynamical transition temperature. Dynamics I will not talk about because I have not discussed that earlier. And then below this TD, there is another temperature where the configurational entropy seems to go to 0 in these models. And there is a true thermodynamic transition at that point. And that transition is described by one-step replica symmetry breaking. So this RSV method that we talked about, in the case of the Renton-Kirkpatrick model, one is to go to this infinitely many levels of replica symmetry breaking. But in this, at least, at temperatures near this TS, one-step replica symmetry breaking seems to be stable. And that seems to describe the behavior of these models correctly. So then there is a lot of theory which is based on this analogy, that the behavior that you see near structural glasses, near the glass transition in structural glasses, then whether that transition, is similar to the transition that one is talking about here, where the configurational entropy goes to 0. And there are, one can use this picture to make some predictions about the dynamics, and there are predictions which seem to give you this Vogel-Fulcher law, etc., etc. So there is a whole class of theories which is based on this analogy between what happens in structural glasses and these other models of spin glass. So I will not go into all of that. And here also this time is gone. So I will not go into too many details, but maybe, if anybody is interested, there's one thing that I might spend some time on is this associative memory. Because this is very similar to spin glass models. And this was worked out by Hoffield. And Hoffield is one of the co-owners of the Maxwell Boltzmann medal this year. And this has a lot of overlap with spin glass theory. So maybe if I have half an hour in the tutorial later today, then I can tell you a little bit about it. Okay. Oh, you're not planning to have the tutorial today. Okay, so if people are interested, I can say a few things about this object model. Yeah. So this is a model which, as I said again, quite old, developed by this John Hoffield. Here, the subject is quite different from what we have been discussing earlier. The subject is basically how we can store some information in a network and retrieve it. So the way that information is stored is in the form of minima. So here, network is basically Ising model, where you have the spins sigma i's and Jij interaction with them. And then one thing that I told you in one of the tutorials is that this Matisse model. Matisse model is this. Well, Jij was some tau I, tau j, where these taus are again plus minus 1 variables, and your interaction Hamiltonian was as before, minus some Jij, sigma I, sigma j, sum over I bigger than j. And this Jij was constructed out of this random variables. These taus are plus or minus 1 with equal probability. And what we showed was that there is a ground state where this sigma I is equal to tau I. Just put in a j here, necessary. If j is positive, and if we have this sigma I equal to tau I for all I, that minimizes the energy, right? Then for every pair, you will have sigma Jij is sigma I tau I, and for tau j and sigma j. So for every pair, that will minimize the energy. So that tells you that there is a way of constructing these Jijs such that sigma I equals tau I for all I. This is a state of the system, is a ground state. Right. So if I want to make a particular state the ground state, a particular state is given by these taus. If I want to make that the ground state of the system, then I'll choose these Jijs in this particular way. And that will ensure that that state is the ground state. So what does it mean? That state is the lowest energy state. So if I now have a network with this Jij, and if I start with a state which is close to this stored state. So this is my stored state. Somebody tells me that I want to store some picture. Picture is given, a picture of a bird is given like that. And this picture is, if you want to call it, if you pixelate this picture, we divide it into pixels, then some pixels will be this dark color and some pixels will be this light color. So dark color, I will say sigma equals +1. Light color, I will call sigma equals -1. So this whole picture can be represented by a string that looks like this. So this is a 2x2 grid. I mean, I have a, not 2x2, I mean, two-dimensional grid. I can have 1,000 pixels this way, 1,000 pixels that way. That's I and j. The pixels will be labeled by this I. And I basically then write down a spin model in which the interactions are like this, where the Jijs I have constructed from the vector that describes the picture that I want to store. So, and if I have a network like that, then if I start with initial state which is close to and dynamics decreases energy. Then, since sigma I equals tau I for all I is the ground state. So if I start with a state which is not quite that, but which is somewhat corrupted, which will have energy higher than the ground state energy. And if my dynamics is that, I'll change a spin only if that spin flip is going to reduce the energy. Then this dynamics will take you to the stored pattern. That's the whole idea that
So the JIJ you constructed from the image.
image, yeah.
Is that okay? And then you're just using that in the whatever dynamics.
Yeah. So JIJ is what I'm saying, that whatever information you want to store, you code it in terms of +1 and -1, that you can always do. And that gives you a string of plus and minus ones, which can be thought of as a configuration of these spins. And that spin configuration will be a minimum of the energy function if I choose my energy function like that, where I put this Jij is equal to tau I tau j. And that will, when I do that, and if then I start with some closed state, which is like this, is a noisy picture, corrupted version of that, which is not quite this sigma I equals tau I, where some of the sigmas have been flipped away from this tau i's. You start here. And then what you're doing is you're flipping a spin only when it minimizes, not minimizes, only when it reduces the energy. So then we'll be coming closer and closer to this sigma I equals tau I, and that is what happens, that this, and then you run the dynamics on that, and you get back the stored picture.
But this could also have some local minima, right? Which it might get.
This, yeah, that will happen. So I was just coming to that. If you just want to store a single pattern, then it is just like Ising model, ferromagnetic Ising model, because I can just define, this is what I did, this Matisse model. If I define sigma I times tau I to be a new Ising variable, then it is just a Ising model in terms of this new variables. So there could still be local minimum. In the ferromagnetic Ising model, if you have a straight domain wall, for example, that is a local minimum of some sort. But then one doesn't have this complex landscape in that case, because if you just want to store one pattern, then that you can map onto the usual Ising model, which doesn't have a very complex landscape. But now the question is, I mean, a network which stores one pattern is not particularly useful. So you want to store some number of patterns. And then if you want to store P patterns, then what Hopfield told us that you have to do this. So for each pattern, we have a Matisse model-like thing that if I put the sigmas exactly equal to those, the taus for that particular pattern, then you have something that looks like a minimum, but that now there is some interference between the different patterns, because your tau I is, oops. Oops, I'm going in the other direction. So then there are, so this is the Hopfield model, where you say that this Jij with some constant, this J doesn't matter, it just sets a scale of energy or temperature, but it is sum of this kind of terms. So there are each tau I alpha, the set represents one stored memory, and you have this Matisse-like construction for every stored memory. So then you just have a, alpha goes from 1 to P. And this is your Jij. Your Hamiltonian is like this, Jij sigma I sigma j, where Jij is obtained from here. And then the issue is that how big you can make this P. One of the issues, how many patterns you can store in this network. So all those things, I mean, there people who have done spin glasses, they can use spin glass theory, because again, you know, you have a Jij matrix, which is random. It's a different kind of randomness than what you have in the SK model. But one can now well, whatever it is. I don't need that very much. So now, you know, this is again a spin glass model. So then you can look at what kind of states that you have in the spin glass. And then there are different kinds of states. This is sort of like the spin glass model where you had a non-zero value of J0. because there are states for which you can define magnetization. So you can define sigma I average, tau I. For each of these patterns, tau I alpha, alpha now goes from 1 to p, and of course I goes from 1 to n. So you can look at the overlap of the spins with a particular pattern. And for good retrieval, you want these m's to be large. So there are now these parameters as well as the spin glass order parameter and things like that. So now you have to have some kind of a phase diagram depending on temperature, depending on what this number p is, etc., etc. And then people have worked it out. And there are many papers on that. And it is still considered to be a good model of memory, how memory works in the brain. Although it is very simplified, but some ideas based on this kind of a modeling, people are still using to understand some brain functions and stuff like that. So just an example from a totally different field where spin glass kind of ideas are useful. Okay, anything else?
Okay, any questions from online people or here? Okay, so no, so then let's thank Chandan for a really great set of lectures. Yes, thank you.